He's probably wouldn't work it. No, he never eats breakfast. I don't know. He's probably just drawing the
All right. Before we kick off, somebody emailed me and pointed out that there appears to be a discrepancy in the exam dates. I don't know how that happened. My UI has the correct exam dates. It looks like maybe my spreadsheet just shifted my dates by one. So right after class, I'm going to go ahead and upload a corrected syllabus that has those exam dates so they match the My UI. Besides that, are there any questions from Wednesday's lecture that I can address before we move on to more review? All right. So we talked on Wednesday, just about what is heat transfer, right, and what are its applications. And one of the things that I kept pointing out is that it has a lot of shared DNA with thermodynamics. All right, thermo tends to be focused on how much energy is transferred, whereas heat transfer is all about figuring out how fast and how much and where and how. And so it's really focused more on the transient side of things and giving us the tools so that we could take a design of something, right? Or we could design something so that we can achieve those quantities that we sort of assumed in thermodynamics. But they, as I said, they share a lot of common theory. Some of those being the laws of thermodynamics. And so we're going to spend today talking a little bit about how we build in that first law of thermo and how that leads us to this idea of heat rate, right? The rate at which energy is transferred as a result of thermal processes. So our goals for today are first to finish relating, right, the first law of thermo to the heat transfer of both open and closed systems. We're going to segue that into this understanding and application of heat flux and heat rate. And if time allows, we will introduce the concept of the rate equation. Though we'll be spending a lot more time with rate equations starting next week. All right, so we've established at this point that the first law of thermo basically states that energy is conserved. All right, that the energy change in a system has to enter or leave the system through processes that include heat transfer, mechanical work, or if you have an open system, that is a control volume where mass can actually enter or leave, then we also can carry energy in and out through the process of advection, right, a fluid flow. But we started to really kind of go through this taxonomy and divide up this idea of energy into all these constituent parts. And that's something I want to review real quick. We did this sort of in a rush at the end of Wednesday's lecture. But we had this idea of total energy, right, which we called E superscript TOT, right, which was made up of our internal energy, U, And internal energy is composed of thermal energy, which we call U subscript T, and other, right? So other, remember, includes things like potential energy due to chemical, okay, electrical charge, or magnetism, right? These are all the things that produce bulk energy in a collection of matter, but which are not thermal in nature. And then thermal energy is further subdivided into, right, sensible energy, U sense, and latent energy, U late. All right, so, and as I mentioned last time, right, sensible energy is that branch of thermal energy that actually causes, right, the temperature to rise. It is what causes increased agitation in the molecules that make up that matter. And so generally, this is what you would be able to detect through, as I said, a rise in temperature, whereas latent energy is that energy that gets caught up in particular kinds of bonds, and so may be expended on going through phase change, right? The fact that as water evaporates into water vapor, right, it loses energy and will actually cool, and that's how we use evaporative cooling, for example. So we've got, right, on the other side here, we have all of our branches of mechanical energy. I'm going to move that down here. We'll call this ME, right, which is made up of our potential energy and our kinetic energy. And I'm not going to go through a lot of additional discussion of those because we should be fairly familiar with the idea of mechanical potential, mechanical kinetic energy. But the reason it's useful to draw this map out this way is because we are going to start to kind of write two versions of the first law of Thermo. The first is the one that we've discussed, right, where it's conservation of total energy. And so last time I tagged this, right, I said, hey, this is sort of our energy quantity number one. But often as engineers, right, we're more concerned with sort of the stuff that is on this side, right? We might be interested in chemical and stored electrical energy or magnetic potential energy, but those things are not going to get built into our first law. We're not really looking at going into the chemical bonds and figuring out exactly how much stored energy some particular fuel source has, for example. We just want to sort of write it in as energy's coming from, right, converting chemical energy into something else. So we're more interested in the thermal and the mechanical. Right? This is really where our thermodynamic analyses get focused. And so we'll take this grouping of thermal and mechanical, basically everything that isn't in this other group. So accepting nuclear, right, chemical, magnetic, etc. And we're just going to call this sum of terms E. So over here we've got E total, and down here we've got E. Now the difference is whether we're including all of this miscellanea that makes up all these types of energy storage. So this gives us our kind of two versions of the first law of Thermo. Version 1. Right, so our E, well, sorry, I spoke. So just to write these out, energy quantities, there we go. Number 1, we've got the stored total energy is our U sense plus U latent plus our U other plus our kinetic energy plus our potential energy. So that's everything in this, right? Our other, our sensible, our latent, our potential, our kinetic. So that's all of our energy sources. And number 2, E stored, where we are missing, right, that total subscript, is our U sense plus our U latent plus BE plus KE, which could be reduced to just U thermal plus U mechanical. Actually, that doesn't need to be. We'll just say plus ME. All right, so like why go through this process? Well, number 1, right, we kind of have to pay attention to, because this is the one that is basically the first law applies to. This quantity has to be conserved, right, because energy is not going to be created or destroyed. It's just shuffled around into different parts of this map. Whereas this is really the more useful branch of energy. This is what applies to our thermodynamic processes, but it's not strictly conserved. So now we can plug these in to get our different versions of the first law of Thermo. So for our total energy, E total, we have over a finite period of time, all right, delta T, we've got that the change in total stored energy has to be equal to, right, the change energy in total minus, right, the net energy out, where, right, these delta E in and delta E out quantities are, like I mentioned on Wednesday, these are composed of heat transfer, work, advection, right? So this is not different from our expression like the Q minus W, right? This, but this does, but this encompasses those, right? We're just saying this is the net change of energy entering or leaving through those processes. So that's applied over a finite period of time, right? Often the more useful, right, is the instantaneous expression. So what applies at every instant in time. Okay, which simply states that the time rate of change of E stored total, which we'll call E dot total stored, is equal to E dot in total minus E dot out total. Okay, so, all right, these are basically parallel statements, right? One applies over a period of time, one applies instantaneously. And we could go on to say that this is equal to Q minus W dot, and if we have an open system, plus, right, E dot as a result of advection. All right. Note, W dot is the rate of work, right? The mechanical power, mechanical work being done per unit time. This is the rate at which energy is changing or entering or leaving our control volume or our open system per unit time. And lowercase q, right? I think that in fluids, for example, you saw this written as Q dot, kind of like W dot. It was a capital Q dot. We're switching nomenclature, okay, over to lowercase q. So I want to make note that Q is equal to uppercase Q dot, but the typical convention in heat transfer is to use lowercase for heat rate, or heat transfer rate. Because we're going to start putting subscripts and superscripts and, all sorts of additional accents on this. And so it helps us to start out more cleanly rather than having a dot already along for the ride. Okay, so this is our total energy. I want to go ahead and make sure we have both of these boxed in. But our second sort of energy quantity, right, E stored, not E total, right, which includes mechanical and thermal energy, has parallel statements. So for finite time, we've got that delta E stored, note the lack of total, is going to be equal to En minus delta E out plus EG. Okay, this is the kind of the special term that I want to make sure we point out. So because mechanical and thermal energy, that sum, is not strictly conserved, right? Because it leaves out the other sources of energy, chemical, stored electrical, etc. We have to include this extra term. And what this represents, okay, is delta EG, or delta right. That transfer of energy from those other sources to this mechanical and thermal. So you say, hey, this battery that we've got on board of our system has discharged or has expended 1,200 joules of energy, right, through discharging and driving some motor or something. Well, this would represent 1,200 joules that get shunted from that thing that we're not counting, right, into the thing we are. It's basically, we're just writing in that other term as a separate, as a separate correction. But it's a little bit cleaner from the engineer's perspective because now you just worry about like the bulk quantity that is being converted from all of these things that are messy and we don't want to deal with, right? We're not here to analyze nuclear bonds. We're not here to analyze chemical stored energy. We're here to figure out how energy moved around between different parts of our system gets us useful results. And no surprise, instantaneous. We get the dt of E stored is equal to E dot in minus, E dot out plus the rate of energy generation. Okay. So for those who, for those of you who recall with any clarity the form of energy conservation that we dealt with in fluids, I like to draw this parallel because it shows that we're not coming at this from completely different perspectives. So when we were dealing with fluids, we said that the net rate of energy, change in energy stored within a controlled volume, was equal to m dot, okay, of basically we said of the thermal energy. We used a U hat in fluids, but we'll transition to our heat transfer nomenclature, plus P over rho plus 1/2 rho V squared plus GZ in minus m dot ut plus P over rho plus 1/2 rho V squared plus GZ out plus Q minus W dot. And we're going to make a slight correction or a slight addition to the fluids version, because in fluids we didn't worry about like chemical energy, right? We weren't thinking of conversion from other sources. That was just something we never considered. And so the only thing we have to do to take our fluids version and make it match is to add that E dot G. Okay. So what we've got here is, right, if this is energy per unit mass, each of these quantities, we've got the mass flow rate times the energy per unit mass. This is the net rate of energy entering our system minus the net rate of energy leaving our system. But this is through the process of advection, right? This is that mass carrying energy in or out without necessarily, so the energy is entering and leaving our control volume through processes that are not heat transfer work, okay, or energy generation. So this is the advection term. Then we have our heat transfer rate, our mechanical work, and our energy generation. And this matches exactly with what we have above if we, right, equal to Q minus W dot plus E dot, right, advection plus E dot generation. All right. I'm going to give you a break from just writing down variations of the same equation. Let's run a few numbers through this to show that these are all actually valid, variations on the theme. So let's consider an electrical circuit, okay, where we have a DC power source, so a battery that is feeding a resistor. Okay. This has a voltage of 24 volts, okay, and is supplying current of 6 amps through the circuit, right, which would indicate that we've got, right, a resistance of 4 ohms. Everything, the whole circuit, okay, all the wires, the battery, etc. Wires and battery are at a constant temperature of 25 degrees Celsius, and the resistor itself reaches a steady temperature of 95 degrees Celsius. Okay, so it's cooking. And we are asked here to find 2 things, or well, really to complete 2 kind of exercises. First would be draw a control surface around just the resistor to determine our E dot in, E out, our E, G, and our E stored. The rates of these quantities. So we're not working with, notice we don't have our total term up here. So we're working with the conservation equation that deals with mechanical and thermal energy. So this is our control surface for A. And then B, repeat the same, right? But considering the entire circuit. So here's control surface B. And our goal at the end of this is we should show that regardless of our choice of control surface, right, our first law of Thermo applies. It wouldn't be much of a law if it was selective about how we defined our control volume or the control surface. So, all right, the quantities that we're working with here, right? What we know is the electrical power, right? We know that this battery is supplying 6 amps at 24 volts, which means that there is 144 watts, right? V times I is power. 144 watts of power coming from the battery. And assuming that our wires connecting the two have negligible resistance, that it's all going to that resistor, okay? Resistors, all they do is sit there and dissipate energy. Okay? They dissipate energy as heat. That's why heaters work. So 144 watts being transferred from the battery to the resistor. Let's see how that shakes out in terms of the equations that we've just written out. So for part A, we've got our E stored is equal to E dot in plus E dot gen minus E dot out. And our control surface is going to include total stored energy inside, right? A rate of energy generation inside. E out leaving, and we can make some guesses that most of that energy leaving is going to be through thermal dissipation, right? And energy entering so remember, these terms include, right, contributions from work, from thermal energy, and from advection. We're dealing with in this case, a closed system, right? There's no mass entering or leaving. So there's no advection, right? No flow. You don't have resistors flowing through this. So we can eliminate that. Our E in, right? We might be inclined to say, well, there's energy entering because there's electrical, right, power being transferred. But remember that without that subscripted total, we leave things like the stored electrical energy out. We're talking about just the mechanical and thermal energy. And so, is there any mechanical or thermal energy entering, right, being transferred from the battery? No. E dot out, on the other hand, right, is there any heat transfer or work occurring that might cause energy to leave? And there, we can make a guess that yes, right? We've been told that this resistor hits a temperature of 95 degrees. All the surroundings are at 25 degrees. So there's probably some heat transfer occurring there. It's not doing any mechanical work. It's not a motor. It's just a thermal dissipator. So we can say, all right, our energy rate in is equal to 0. Right? No heat transfer, work, or advection into our system. Our rate of energy generation, okay, this is that transition. At what rate are other sources of energy being converted into mechanical or thermal? And this is where the influence of the battery comes in, right? Because there is a 24-volt jump across this and current flowing through at 6 amps, which means that there is 144, okay, 6 by 24, 144 watts of total energy entering, but it enters as electrical, okay, power. I should say not energy, electrical power. And is inside of the bulk of this resistor is converted from electrical to thermal. So the energy generation is 144 watts, right? Part of that other group to thermal. That energy storage, okay, this is one that we have to pay attention to the way the problem is phrased, because we're told, all right, that the resistor hits a steady temperature of 95 degrees. So its internal thermal energy is not changing anymore. It's at a rock steady 95. It's not going through any phase change. Okay? There's nothing transient about this. It's not accumulating any more energy, right? If this were in the process of heating up, that would be different. We would be accumulating thermal energy. But it's at steady state, and so looking at our conservation law here, right, we've got 0, 0, 144 watts, which means that our E dot out has to be equal to 144 watts. Makes sense. There is 144 watts, right, being transferred from the battery to the resistor and then being dissipated through the process of heat transfer. It's which means that this is all occurring through our Q term. So that's the heat transfer out of our system. So nothing really that remarkable here, but we've shown that we can take a familiar system and represent it through this version of the first law. Let's really quickly do the same. We won't spend as much time on explanation. But for the entire, right, for the entire circuit, so if our control volume looks like this, we've got our battery, our resistor. And so in the battery, right, we're going to have some energy generation, right? Or sorry, take that back. In the battery, we're having a process through which energy is changing types, right? A battery converts chemical energy to electrical energy. That resistor we've shown, right, is converting our electrical energy to thermal energy. And so really what we've got here is sort of a chain, right, where it goes ultimately inside of our control volume. We're going from one other energy type to another other energy type, and then finally into our thermal plus mechanical. So all of this process can be represented by a single energy generation term. EG still is 144 watts. Okay. I just want to make it clear that this is because that energy isn't being converted to thermal, right, at any place except the resistor. En remains 0, right? E dot out is still 144 watts, and E stored, or E dot stored, is still equal to 0. And so we have, once again, right, this balance between the energy being generated, okay, or converted from other to thermal and mechanical, and then dissipated through heat transfer out of the system. E stored is equal to, right, Q minus W plus E N 0, okay, minus 144 watt plus 144 watt minus 0. All right, so it's also important that we understand not just how much is entering and how fast, but we also want to be aware of where this energy transfer is occurring. And this is a good lead into that, because we saw, particularly in part A, I did this on purpose. Note that our E dot in and E dot out are shown as things like entering and leaving, and our E dot stored and E dot gen are written inside of our control volume. It's because these represent really two different types of energy transfer: volumetric versus surface. So this is fairly intuitive, right? Volumetric energy is energy that is distributed throughout matter. And so if we think of the total stored energy of matter, we understand that that's going to be kind of everywhere. With energy generation, we think about a resistor. Okay, it's some collection of matter that has electrical resistance. That resistivity means that as current flows through it, it generates heat kind of uniformly throughout its volume. So that is a volumetric energy generation. But if we're talking about heat transfer in or out, or if we're talking about work in or out, usually that is energy that is only transferred to a system from outside in, or vice versa. It has to go through the surfaces. Okay. That resistor might generate thermal energy all throughout its volume, but it can only get rid of it by transferring it out through the outer surface of that resistor. And this is really important because this is going to affect how we analyze things that are vanishingly thin. So volumetric energy or volumetric phenomena, we won't are those that are distributed throughout the bulk, right, of a collection of matter, and surface phenomena occur, right, only at surfaces. So, right, for volumetric, we might see energy conversion, right, from, for example, electrical to thermal, as we saw with the resistor. And for surface phenomenon, we might see, something like heat being radiated from some cooling fins that are installed on that resistor. All right. I'm going to skip over some of the special cases here because those are, I think, not really necessary to cover at the moment. I want to talk for a moment about heat flux and heat rate. I think we're a little burned out on first law. So we've seen, right, through up to this point that Q is a parameter of significant interest. So we can say that instantaneous conservation of energy is important for applications to, from figuring out how quickly resistors are generating thermal energy to how quickly you're discharging batteries to everything in between. And so our focus in this course, okay, is going to be on one particular part of that. So we've got E dot stored is equal to Q minus W plus E gen plus E dot advection. So if fluids, sort of said, all right, these two are given to you, but this advection term is our obsession. Okay. In this class, we are all about that Q, right? So we're going to be spending our entire semester focused on figuring out that heat rate. Q is the net rate of energy transfer through the modes that consist of conduction, convection, and radiation. All right. Here's the new one. I want you guys to pay attention. This Q double prime vector. All right, we've added a whole bunch of, there we go. This is related to our heat rate, but is a little bit more of a detailed quantity. This is what we call our heat flux. And this is, right, the rate of heat transfer per unit area normal to that area. Okay. So if our total heat rate is in, right, joules per second or watts, our heat flux is in units of joules per, right, second meter squared or watts per square meter. The reason we've got both of these is we are interested in this Q, but most of the time it's this heat flux that is we're going to be able to calculate directly, right? this is what's going to depend on things like thermal temperature gradients, or the angle of a surface relative to fluid flow, or the sight line to a source of radiation like the sun, is we're going to be starting from heat flux and relating that to our physical system, and then going from heat flux to heat rate through integration. So Q is equal to, the double integral of our Q double dot vector dotted with the surface normal, integrated over an area. And so our net heat transfer rate is a scalar quantity. And Q double prime, our heat flux, is a vector, meaning it has Q double dot X, X, Y, and Z components. Plus Q double prime Z. So in other words, our heat transfer rate is the net sum of all of our heat flux across the surfaces that we're considering in a given problem. All right, I'm going to give us the setup for a problem that we will revisit as a warm-up on Monday. It's going to deal with heat rate and heat flux. I want us to consider a wind turbine. This is kind of a stumpy looking wind turbine, but not shown to scale. And so inside of this turbine's what's called the nacelle, that is the cylindrical housing, live first a gearbox, and then a generator. And we're given the following information. The nacelle is a cylinder with a length of 6 meters and a diameter of 3 meters. The gearbox has an efficiency of 93%, and the generator has an efficiency of 95%. So basically, wind turns the blades, we get mechanical energy entering, we get 93% of that mechanical energy out of the gearbox into the generator, of the mechanical energy into the generator, we get 95% being turned into useful energy. Where does the rest of that energy go? Heat. Inefficiencies are conversion into thermal energy from whatever. So, let's see. The generator produces a power at a rate of 2.5 megawatts. We are asked then to find, first, the net rate of heat transfer, we'll say of heat required for steady operation. Basically, how much power has to be dissipated through the nacelle in order for this thing not to just keep rising in temperature till it cooks itself. And what is the heat flux? across the nacelle surface. So we're going to use the first law to answer part A, and then we're going to use this definition of heat flux as the heat rate per unit area, as well as the known geometry of the cylinder to figure out how much surface area there is, and to answer part B. So we'll pick this up on Monday. I'll have this up on the projector, and we'll work through the solution. Hope you guys have a good weekend, and we'll see you next week.